Hello. Um, this example, this video is an example of reduce and return and how to do reduce and return. So we will be finding VAB, VA, VCB, and I1 using the reduce and return method. So we're going to go ahead and get started. So in reduce and return, so what you're trying to do is you're trying to reduce the circuit into a voltage source and a resistor, and then make your way back, work your way backwards and find all the values for the current as well as the voltage. So let's get started with this. So here we have R4 and R5 in series. So what we're going to do is we're going to combine these two, and the biggest resistor name that we have here is R8. So our next resistor would be R9. So we're going to go R9 is equal to R4 plus R5, and then what we're going to do is we're going to move it. Oh, let me try that again. I'm going to move it a little bit this way, and so that's going to be our R9. And we know that in series circuit the current is the same, so IR9, IR4, as well as IR5. Okay, I'm going to go ahead and plug these numbers in. 1.2 kilo ohm plus 1.8 kilo ohm to give us a value of 3 kilo ohm as R9. Okay, so now that we've done this, what we're going to do is we're going to combine these two and we're going to redraw our circuit. And when we redraw our circuit, we come up with this as our new circuit, which is R9. And R9 is pretty much in parallel with R6. So they're sharing the same node here. They're sharing the same node there. So what we're going to do now is we're going to combine these two resistors because they're in parallel, right? So our last resistor was R9. Now it's going to be R10, which is going to be R9 multiplied by R6, and then R9 plus R6. And we know that the voltage for these two are exactly the same. So we can say that VR10 is equal to VR9, and then VR6 is also equal to VR9. So in parallel circuit, the voltages are the same, but in series, the currents are the same. Okay. So now what we can do is we're going to combine these two resistors into one and redraw our circuit. So as I go down, you can see that now R10, these two resistors have been now combined, and now R10 is our new resistor. So R10 is in parallel with, R10 is in series with R7. So our last resistor was R10. Our new resistor is going to be R11 is R10 plus R7. Did we write the value for this? No, we haven't. So we're just going to go back and write the value for this. R9 was, what was the value for R9? R9 was 3 kilo ohm. So 3 kilo ohm. And then R6, the value for R6 was 8.2. Okay. 3 kilo ohm plus 8.2 kilo ohm, and then what we're going to do is we're going to calculate this and we get 2.19 kilo ohm. Okay, R11. So now we can find out what R11 is. R11, so we know what R10 is based on our previous answer, which was 2.19 kilo ohm, and R7 is given in the problem, which is 3.3 kilo ohm. Okay. So now we can calculate what R11 is by adding these two together, and we would get 5.49 kilo. Let's not forget that these two resistors are in series, so that means the current for IR11, IR10, as well as IR 7 are the same. Okay, so now what we're going to do is we're going to combine R10 as well as R7 together to come up with a new circuit. And you can see that, let me just erase this color to show you what happened to the, so now when we move, when we combine R10 and R7, we get R11, which is, this is our new circuit. So I'm reducing the circuit as we go, and I'm showing all these circuits as well, right? So now it's R12, the next one, so R12. But we have to look at it and be like, okay, is R11 in series with R8? No. Is it in parallel? No. So the next thing is to check to see if any other resistors are in series or parallel. We can see that R2 and R3, they're both in parallel to each other. They're in parallel. So they're sharing the same node. There's a node here. There's another node there. So they're sharing the same node. So what we're going to do is we're going to say R12 is equal to R2 multiplied by R3, and then R2 plus R3. Did we calculate that? Yes, we did. So now R12 is R2, which is the value of R2 was 6.8 and R3 was 5.6. So we can go ahead and say 6.8 for R2, and then 5.6 for R3, and then we do the same thing for this one. I didn't write the unit up top, but you'll know that it's kiloohms. And then R12 is equal to 3.07 kiloohms. And since this is a parallel, since these two are in parallel circuits, they're in parallel to each other, so the voltage of VR12, VR2, as well as VR3 are exactly the same. So now what we're going to do is we're going to combine these two, where we get R12. And looking at this, we see that we have R12 now as our new resistor added to this. So now we're going to include R11 and R12. They're going to be in series, so that's going to be our new circuit. So new resistor. R13 is going to be R12 plus R11, which R13 is equal to R12. We calculated in the previous step, which is 3.07 kiloohms, and then R11 is going to be 5.49 kiloohms. 5.49 kiloohms. And if we add those two together, we would get 8.56 kiloohms. And again, this is in series, so that means that the current for IR13 is exactly as the current for IR12 and IR11. So these currents are all the same. The next step is to combine these two, make it into one resistor, and we'll call it R13. And then we know that R13 is our new resistor that's been added. And now we can show that R13 and R8, they're sharing the same nodes, so they're in parallel. They're sharing two nodes the same, two same nodes, and then they're in parallel. So then R14, so our last one was R13, now it's R14. It's going to be R13 multiplied by R8, and then R13 plus R8. And then if we calculate this, and then we can come up with the answer to this. 8.56 is R14, and R8 is from the problem. It's 4.7. We can extract that from the problem. It's 4.7 kiloohms. And then these are 8.56 plus 4.7 kilo. And we get a value of, for R14, we get 3.03 kilo. Okay, so now what we do is we combine this and this into one resistor. And we're going to call that resistor R14. Right? We're going to call that resistor R14. But now we know that R15, which is going to be our new resistor, is going to be R1 plus R14 because they're in series together, right? And then these ones would have these resistors would have the same current. So IR1 is going to have the same current, IR14 is going to have the same circuit. So, current. So we're going to go ahead and calculate what R1 is. R1 is, we can get it from the problem. Scroll up all the way, we get 1.5 kilo ohm. And then we can go ahead and write that in, 1.5 kilo ohm. And then R14 is found from the previous answer, which is 3.03 kilo ohm. And if we add that together, we get 4.53 kilo ohm, which R15 is equal to our, we'll say, this is our last resistor that we're combining, and then we can tell that R15 is equal to 4.53. But we also know, so we're pretty much reduced this circuit from this to only, so we can pretty much stop at this point, but to prove the point, what I'm trying to say is that it's only a single resistor and a single voltage source. So now IS is pretty much equal to all this. Okay, now that we know R15 and we know what VS is, we can find out what IS is. So IS is calculated by going IS is equal to VS divided by R15. And then VS is equal to what? 40. And then R15 is found from the previous answer. It's equal to 8.82 milliamps. So now we're going to work our way backwards and find out what the current and voltages for each part, for each resistor is. Okay, so we're going to go back here and we're going to say that this is equal to 8.82 milliamps. So now that I know, oh, I forgot to put this one. We should know that this is VR14, VR13, and VR8. They're equal to each other. So now that we have this 8.82 milliamps, we can pretty much find the values for this voltage, for this current, for this voltage, and so on and so forth. Okay? So I'm going to show you how we can find that. So we know R14. We're trying to find out what VR14 is. We know what the current through R14 is, so we can find out what VR14 is. So VR14 is equal to IR14 multiplied by R14. So IR14 is 8.82 milliamps multiplied by R14, which we're getting it from here, 3.03 kilo ohm. And we find that VR14 is equal to 26.7 volts. So now we can write this right beside this. So this way, VR8 is 26.7 volts, VR13 is 26.7 volts, as well as VR14. Okay, going to the next one. So we got IR13, IR12, IR11, and we know the resistance value for the 13 for the resistor 13, we know it's 8.56 kilo ohms. We're trying to find out what the current for that through that resistor is, and we know what the voltage is, so we can definitely find out what the current for IR13 is by going VR13 divided by R13. So VR13 is 26.7 volts. R13 is 8.56 kilo ohms, and then we get a value of, for current, we get 3.12 milliamps. So then we can say that all this is also equal to 3.12 milliamps. Okay, moving on to the next one, which is VR12. So we're trying to find out what VR12 is. VR12 is equal to IR12 multiplied by R12. So IR12 is coming from here. So then it's equal to 3.12 milliamps. And then we know what R12 is. It's 3.07 kilo ohms. And then we can find out what this value is. And we calculate it to be 9.58 volts. So we can say that this is also 9.58 volts. Okay, all right. Okay, so this is R11, this is a 10. Maybe it doesn't see, you can't see it clearly. So I'm just going to rewrite that. Okay, so now we want to find what IR11 is. So let me just go back to the same color. IR11 is equal to VR11 divided by R11. So VR11, do we have VR11 here? No. Do we have IR11? Oh, we do. We already have what IR11 is. It's the same current as this, so we don't have to do this. We can just go ahead and write down 3.12 milliamps. Easy. Okay, next one. Here we're trying to find what VR10 is, which is IR10 multiplied by R10. IR10 is 3.12 milliamps, and I got it from here, multiplied by R10, which is 2.19 kilo ohms, and we calculate a value of 6.83 volts for VR10. And the last one, which is IR9, is going to be VR9 divided by R9, and we already know that VR9 is equal to 6.83 volts, so we can go ahead and write that there and come up with our R9, or R9 is already 3 kilo ohms, and then come up with our IR9, which is equal to 2.28 milliamps. So now that we've found everything, so this is pretty much reduce and return. So we found the value for the current and voltages for all the components in this circuit. Now what we do is we want to find out VAB, VA, VCB, and I1. I'm going to go ahead and show you I1 first. So looking at I1 here, we have this current here, which is called IR1. We also have this current here, which is called IR2. What we're going to do, I'm just going to erase this. What we're going to do is we're going to do KCL. So we're going to say the current N should be the sum of the current going in. It should be equal to the sum of current going out. So I should include being sloppy a little bit. Okay, let's just write that nicely. Okay, what's going in? So IR1 is going in. IR2 and IR1 are coming out from node A. So I'm going to, so this way I don't have to worry about the positive and negative, and I can just rearrange it. So now I'm going to rearrange and solve for I1. So I'm going to move I1 to this side. Sorry, I'm going to move R2 to this side and then leave I1 there, but I'm just going to rearrange it and write it this way so it makes more sense. So I already have the value for IR1, so I'm going to go ahead and find where IR1 is. Searching for IR1. IR1 is 8.82 millivolts, and then IR2 is, we can come back to that, 8.82 millivolts, 8.82 milliamps. Did I say millivolts? Milliamps. Yes, milliamps. And then IR2, do we know what IR2 is? We don't know what IR2 is, but we do know what the voltage for R2 is. So we can take this voltage and divide it by the resistor R2, and then we can find out what the value for that IR2 is. So 9.58 divided by 6.8. And then if we do this calculation, So then we should get 7.4 for our current going through this point in circuit. So 7.4 milliamps. Okay, so we found that. So this is good. We can check that. Now let's find VA. So what I'm going to do is I'm going to take a snip of this